Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. Tonight, we're going to examine different scientific mysteries. By scientific mysteries, I mean phenomena, observations, or hypotheses that science has had a hard time figuring out or that are controversial. Things like the origin of this hellish climate on the planet Venus, or the origins of gigantic black holes at the center of every galaxy, or closer to us, deep sea gigantism, the fact that many species living deep underwater tend to be bigger than their cousins near the surface, when theoretically, the scarcity of food and energy in the abyss should point to the opposite. They should be smaller. Don't worry, this may sound a bit complicated, but it will all make sense. The concepts are easy to grasp, so if the concepts can be understood easily, why are these questions mysterious? Because their origin, how they appeared, or the way they work are harder to fully understand, which doesn't invalidate scientific knowledge or the scientific method. Quite the opposite. Science advances by solving questions and facing challenges to existing theories. So, what we're going to do is review some of these mysteries. I'll explain why they are mysteries in the first place. What possible hypotheses could explain them, and how they question our understanding of the world, or open doors that could further it one day. That gives us a lot to talk about, and this is going to be another long dive. But first, I would like to let you know that we have a Patreon page for those of you who wish to and can support this project. Get more of it and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3.50 per month, but it doesn't mean you get less. We let people contribute what they wish to or can, and everyone gets everything that is on our page. Because the world is a better place when the sun shines for everyone. You will gain access to several exclusive episodes as well, and you can listen to and download all the episodes with and without background sounds. And as a token of gratitude, we offer advance releases to our patrons. We have added links to Patreon, as well as links to different streaming options, which may be better suited for you. But before we begin, let's take a moment together to prepare for our journey ahead. If you'd like, gently close your eyes and let your daily concerns drift away. Find a position that feels natural and cozy. Perhaps make small adjustments until you're perfectly comfortable. Now draw in a deep, nourishing breath, and as you release it softly, notice how your body responds. Feel the warmth flowing from your neck down through your shoulders, melting away any tension. Let your facial muscles become soft, your jaw loose, your fingers naturally open, and your legs completely at ease. And as you settle into this peaceful state, my voice will be your gentle companion as we begin our exploration together. Let's start with our first scientific mystery. As you know, galaxies like ours, the Milky Way, are gigantic clusters of stars, some small, some enormous, and around them plenty of other celestial bodies, planets that often form and stay around the star, asteroids, comets, enormous clouds of gas and dust called nebulas. This is where it is believed star systems form when parts of these nebulas collapse on themselves due to gravitation. And there are also former stars and galaxies that have turned into extremely dense bodies after they have burnt their fuel. These dead stars, when they are about the size of our sun, tend to become objects called white dwarfs. If they are bigger, they may turn into neutron stars, and very big stars turn themselves into black holes. I've told you about black holes in various previous stories, and most of the time, when we talk about the formation of black holes, this formation is explained by the collapse of a massive star on itself. You know that black holes are incredibly dense celestial objects from which nothing can escape, including light, which makes them hard to spot with telescopes because they emit no light. But their very strong gravitation can betray their presence. They are such a dense pile of matter that they attract and can capture other objects on orbits around them. It is believed that our galaxy is home to many black holes, remnants of dead supermassive stars that could no longer resist collapse on themselves because they had burnt too much of their fuel. What does it mean exactly? A star is not like a rock. It is a ball of matter, mostly hydrogen and helium, and it emits heat and light because of fusion reactions inside it. Hydrogen atoms are subject to such strong pressure and high temperatures that they fuse, they merge, they turn into heavier atoms of helium, generally. These fusion reactions generate a huge amount of excess energy. The fusion reaction of hydrogen atoms is called exothermic. It releases energy in the form of radiation, such as heat, light, and also kinetic energy particles that are expelled at high speed. So when a star like the Sun, or a bigger one, is in the sequence of its life, when it shines by fusing its hydrogen, it lives in equilibrium. On one hand, there are the constant fusion reactions and the pressure of matter that resists being compressed. These tend to make the star expand. But on the other hand, there is gravitation that plays in the opposite direction. Gravitation tends to attract all this huge quantity of matter towards its center and compress it. So the size of the star is the product, the result of these two main opposing forces. This equilibrium is called hydrostatic equilibrium. But when the star ends its life, meaning hydrogen becomes rare inside it, and heavier atoms begin to fuse, like helium atoms, its release of energy increases, and this may cause the size of the star to grow dramatically so. Maybe you heard that it is expected that one day, in several billion years, when the sun finishes its main sequence, it will grow dramatically and could even absorb our planet. This is what models suggest for the end of a star like ours. This expansion can even turn, for big stars, into a sudden explosion, and this is what is called a supernova, a release of energy so immense that the star is crushed, and with it, the system around it, leaving only a giant cloud of matter. It is believed that heavier atoms, like carbon or oxygen, all the way up to heavy atoms like uranium, form in these supernovas as the fusion products of these last moments of a large star. But matter never disappears after this phase of expansion and eventual supernova for larger stars. The remains of the star are now subject to gravitation, without the expansive force of fusion reactions to counterbalance it. So this matter comes together under the effect of gravitation. It accretes and forms a dense body, much denser than the star ever was. Depending on the previous mass of the star, this new body can be a white dwarf, a relatively small body, or a neutron star, which contains more matter. Or, if there is enough matter, it can turn into a black hole. This is why not all stars turn into black holes, only the bigger ones. So, in summary, this is how the formation of black holes is generally explained. But separately from this theory, there is another type of black hole, one that is much less discussed, at least among the public. There are much bigger black holes, the ones that are at the center of galaxies. Why different? Because their size, their mass, the quantity of matter they contain is just on another scale. These supermassive black holes have masses ranging from millions to billions of times the mass of our sun. There is just no way their mass could come from the collapse of a single star. One of the largest known such supermassive black holes was detected several billion light years away from us. It is called TON 618, and estimates of its mass vary from 40 to 60 billion times the mass of our sun, and that defies imagination. Despite the extreme density of this body, it would still have a radius of more than 1,000 times the Sun-Earth distance. Not all supermassive black holes are that big, but they are at least several million times more massive than the Sun. For example, our galaxy's central black hole, which is called Sagittarius A star, because viewed from Earth, it is located near the constellation Sagittarius. So this black hole is estimated to be about 4 million solar masses, 4.3 million times as massive as the Sun precisely. How do we know it? Not by precise measurement on sight, obviously. Mankind has never gone that far. But by observing the movements of bodies around it and how they react to its gravitation. From this, its mass could be detected. Due to its extreme density, there are more than 4 million solar masses compacted in a space of only 17 times the Sun's diameter. That's also an estimate that will be subject to revisions because these estimates for Sagittarius A star are quite recent. And all of this to finally get to our mystery here. Where do these supermassive black holes come from? Because clearly, not from the collapse of a big star on itself. That would not be sufficient by several orders of magnitude. What kind of initial set of conditions or what history of absorbing other bodies, maybe, could lead to black holes millions or even billions of times more massive than the ones that appear after a supernova? And also, did these supermassive black holes appear before galaxies, which would have formed from other bodies starting to orbit around them, or after galaxies, as a result of millions of stars being absorbed at the center of the galaxy? It is a bit like the egg and the hen. Which one came first, the supermassive black hole or the galaxy? This is still a topic of active debate and research among astrophysicists, and several leading theories about the formation of these giant black holes have emerged over the past decades. The first theory is that massive clouds of primordial gas collapsed on themselves billions of years ago, and they were so gigantic that instead of forming stars, like in most astrophysics models for the formation of star systems, these clouds went straight to black holes without going through the star formation process. It is seen as possible in regions of the universe with high gas density and certain physical conditions, like the ones found in the center of early galaxies. The second hypothesis is called the stellar seed theory. Here, the idea is that instead of forming immediately as supermassive black holes, these gigantic black holes appeared as remnants of the first generation of stars. The first stars to form after the beginning of our universe, more than 13 billion years ago, according to the Big Bang Theory. The first generation stars are believed to have been quite massive and rather short-lived. Short-lived for a star still means millions of years, but the bigger a star is, the shorter its main sequence tends to be. The main sequence being this part of its life when it shines. Why is it so? Because their consumption of fused hydrogen increases exponentially with their size. So, the bigger they are, the faster they tend to burn their reserves. For this reason, these first generation stars would have ended in supernovas, given their sizes, and after that, turned into quite massive black holes that would have become the seeds of galactic black holes. After that, over billions of years, these initial seeds would have grown by accreting more matter. The black hole absorbs matter and does not let it escape. That's its very definition. So it can only grow in mass, or these seeds could have merged between them too. During galaxy mergers, when two galaxies crash into each other and form a single one. This long process would have gradually increased their mass to supermassive scales. So, theory number one is that supermassive black holes appeared as such from giant gas clouds. Number two is that they grew from seeds left by the first stars. And number three is that they grew from several regular black holes. They would be the product of a long accretion process. And instead of a stellar seed, the process would have been kick-started by the merger of multiple black holes near the center of galaxies, where the density of stars and star systems is higher. Then there is a fourth, more speculative hypothesis, which is considered speculative because it is purely conceptual. There are no observations or models that point to it. It would be that all, or some of the galactic black holes are primordial bodies that would have appeared in the early universe, even before stars or nebulas formed. In this early universe, which was smaller, hotter, and much denser than today, and just beginning its expansion, there would not have been fully formed bodies yet, but there could have been fluctuations in density, like clumps of matter, and these would have become the supermassive black holes around which billions and billions of other bodies would have gathered due to their gravitational force, forming galaxies. It is just an idea, and as such, it is hard to confirm or refute. But in this hypothesis, galaxies would have formed after supermassive black holes, not before or at the same time. These black holes would have created their galaxies by attracting other bodies. So this is the summary of this mystery, and given how far and interestingly hard it is to observe the supermassive black holes are, it is likely that it will not be fully solved anytime soon. However, it should be mentioned that maybe not every galaxy contains a supermassive black hole at its center. It is believed that the vast majority do, if not all of them. But there are different types of galaxies, some that are called dwarf galaxies, and that are smaller, independent clusters of stars that have not always been proven to have one. But they could be smaller, logically, and less detectable for that reason. There is also a concept called ultra-diffuse galaxies, which, as the name says, faint and spread out galaxies. Their density of stars and their movement make them markedly different from spiral or elliptical galaxies like ours, and the majority of known galaxies too. These ultra-diffuse galaxies are somewhere between a regular galaxy and a cloud of objects. They are like regions of the universe with a higher density of objects, and in their case, it isn't sure if they have a supermassive black hole because they don't have an obvious center. So they may contain plenty of smaller black holes that resulted from the death of large stars. But there is no systematic evidence that they have one supermassive hole that keeps them together. Our second mystery of the night will take us back to Earth. But don't worry, We'll go back to space after that when we explore the planet Venus. Have you ever heard of deep sea gigantism? This term refers to a particular phenomenon. It has been observed that not all, but many species of marine animals living in the deep ocean grow to significantly larger sizes than their relatives in shallower waters. In other terms, the deeper they live, the bigger they tend to get. And this is intriguing because supposedly an animal species would reach a larger size where it has access to more resources, more food, be it under the form of plants or prey, more heat and light, maybe more competition with other species, which pushes some of them to occupy the top spot in the food chain by becoming large predators. But the abyss, deep down the oceans, seems to be the opposite environment. It is scarcely populated. The density of prey is very low. There is no light, so plants cannot practice photosynthesis. And so there are no plants to eat unless they fall from above. There is a bit more life near the seafloor, but away from it, fish or invertebrates like squids could sometimes spend days or even weeks without crossing any other animal. So why, in such a poor environment, when it comes to food and energy, can some species grow so much and more than in other more favorable places? Before we take a look at a few examples of deep sea gigantism, like giant squids or isopods, let's examine the possible factors behind what is still not perfectly understood, the possible explanations to such a counterintuitive phenomenon. A first factor, and I'm going to mention at least a half a dozen, but this is just the first one, may have to do with lower temperatures. The temperature of water is stable in the abyss. It tends to decrease slowly when you go down under the surface, and after a few 100 meters of depth, it stabilizes slightly above 0 degrees Celsius, or between 32 and 37 degrees Fahrenheit. Such a temperature would be a problem for warm-blooded animals like us mammals, but inhabitants of the abyss are generally cold-blooded. Their temperature varies with the environment, and the lower body temperature than their cousins near the surface means that their metabolism slows down. Less energy is needed to sustain the basic functions. This could have two consequences. First, a slower metabolism tends to increase their lifespan because they also age slower, and a longer life means more time to grow. The slower metabolism could also leave more energy available to grow, since less is required to sustain basic functions. So these two factors could contribute to bigger sizes. Apart from lower temperature and metabolism, a second environmental factor to deep sea gigantism could be the relatively low levels of oxygen in water at this depth. Some researchers have suggested that gigantism could be an adaptation to the relative scarcity of oxygen, because larger bodies might need less oxygen per unit of weight or tissue than smaller organisms. This means that larger bodies at this depth could breathe better and need less effort to oxygenate their blood, which would put them at an advantage. Size may also be an advantage for a third reason, which is the scarcity of food. Sounds counterintuitive. If there is not much food, then animals should be smaller. But in reality, in an environment where nutrients are scarce and arrive sporadically, for example, when a large carcass falls or when marine snow, this organic matter falling down from above, intensifies. In such an environment, it is advantageous to be able to store more food and more energy. A large stomach and layers of fat are perfect to quickly take advantage of food opportunities and survive long periods without food. Larger animals also tend to be metabolically more efficient. In other words, the bigger you are, the better you conserve energy, in part because you lose less temperature. The surface exposed per unit of weight is less than a smaller animal. If you think of a large polar or cold water species in general, like seals, whales, or polar bears, they tend to have short limbs on big, smooth bodies that are efficient to minimize heat loss. An animal that is not really an example of deep sea gigantism, but illustrates some of these points: life at low temperature, slow metabolism, long lifespan, large body, is the Greenland shark, also known as the gray shark. It is rarely spotted because this species of shark lives in the depths of the northern Atlantic Ocean, typically between 100 and 1,200 meters. That's 300 to 3,600 feet underwater. They are not the biggest sharks, but they are quite big, with an average size of 4 to 5 meters, around 15 feet. But what they are remarkable for is their incredibly long lifespan and their slow metabolism. They are estimated to live 250, 500 years, meaning that they are probably a few older Greenland sharks out there that were born in the 16th century. They can start to reproduce. They reach sexual maturity at 150 years of age. The development of their young inside the mother's womb takes 8 to 18 years. They do everything very slowly. And with their large bodies that can store energy and burn it very slowly, they can survive a month between meals, which makes them well adapted to the rather unpopulated open waters where they live. So this species of shark is a good example of adaptation to cold waters and high depth, thanks to very slow metabolism and a long lifespan, and also a relatively large size that helps them store energy for long periods of fasting. Now, a fourth possible factor that would contribute to deep sea gigantism is the limited predation. There are predators in the depth, but not many. And this means that the odds of living longer and of growing more look better. But also, organisms and their evolution do not necessarily need to prioritize traits like agility or speed, which generally are characteristics that come at the expense of size. So, with less pressure from predators, they may have evolved. They could have been selected under other constraints that made a bigger size possible. And finally, yet another factor could be that larger organisms are better equipped to withstand the pressure. Now, as you know, pressure at several hundred feet underwater is huge and would crush any surface organism. Animals populating the abyss do not bear that pressure like a submarine would do. They don't have air inside, and instead, they embrace the pressure around them. Their bodies are at a similar pressure to their environment or close. But still, they change depth, and not every single inner part of their bodies can adjust to pressure. This is where a bigger body with more robust structures can be advantageous. It allows for larger, fluid-filled cavities inside their body, and with that, plenty of advantages. For example, with a part of your body that can withstand some pressure, you can develop senses that tell you at which depth you are, which can be useful for hunting prey, finding mates for reproduction, or just piloting at which depth you live. So it is probably a combination of these factors that explain deep sea gigantism. Now, what does it look like concretely? Let's take a look at examples, starting with a crustacean called Venusian gigantism, which is an isopod, an order of crustaceans that have 7 pairs of legs and a flat, segmented body. Some have adapted to living on land, like woodlice that you may find under stones or logs in your garden. Venusian gigantism looks a lot like a woodlouse, but it is 12 to 20 inches long, longer, 30 to 7 centimeters, and it weighs up to 1.7 kilograms, close to 4 pounds. No isopod of such a size is known on land or in shallow water. It is very large. This species lives typically in depths from 1,000 to 7,000 feet on the ocean floor. And, like many deep sea species, they can be found around the world. Their distribution is worldwide in the Atlantic, Pacific, and Indian Oceans. It is logical because the set of conditions at more than 1,000 feet underwater tends to be the same everywhere. Same temperature, same absence of light, so the same food chains. And that's why many of these abyssal species have a worldwide distribution. At the depths where they live, they find about the same environment in all oceans. So, Venusian gigantism live on the seafloor and spend most of their time scavenging for food, feeding on carcasses that fall from above and marine snow. It has many of the characteristics I went through before, like the ability to fast for months and to gorge itself when it finds something to eat. Some reports suggest they can live up to 5 years in captivity without a meal. They also have a very slow metabolism. They never spend much energy, and instead they move very slowly. Another example of a deep sea giant is the giant squid, and also its cousin, the even bigger colossal squid. The giant squid typically lives at 1,000 to 3,300 feet. That's 300 to 1,000 meters deep. But occasionally, it ventures closer to the surface. And this is probably why it has been known to men for thousands of years. It is believed to have inspired the kraken, the mythological monster, or more recently, it appeared in 20,000 Leagues Under the Sea. If we include their tentacles, they can reach up to 18 meters or 60 feet. For females, which are bigger, males reach only 10 meters, and females can weigh up to 600 pounds, 275 kilograms, which sounds relatively light for their length. This is because their tentacles are rather thin. Their bodies themselves, excluding the limbs, are shorter, about 8 feet or 2.5 meters. They are also famous for another characteristic. They have the largest eyes in the animal kingdom. Their eyes can be up to 27 centimeters or 11 inches in diameter. These huge eyes serve to spot prey in very dim light, prey or predators. They have a famous predator, the sperm whale, which feeds on them. Giant squids are much larger than their shallow water equivalents. And here again, it is believed that they acquired their size due to their life in the abyss. They are also believed to live longer than other squids, 5 years or more, which doesn't sound like a lot, but all squids have short lifespans. Even more impressive than the giant squid is the colossal squid, which has unique features. First, there's its distribution. It lives primarily in the southern hemisphere around Antarctica, and it resides deeper than the giant squid, at more than 1,000 meters deep, or more than 3,300 feet. In length, colossal squids are shorter than giant squids, but they are much bulkier and weigh almost twice as much, up to 500 kilograms, or 1,100 pounds. So here we have another example of an animal that lives deeper and is also heavier. They also have rotating hooks on their feeding tentacles that are unique to this species. And logically, for such a deep-sea species, they favor energy saving in their feeding strategy. They are thought to be ambush predators that wait rather than actively chase prey. They feed on deep-sea fish in particular. I said they are thought because obviously this species is hard to observe in its natural environment for obvious reasons. But here again, the bulkier body, the larger size, and the slow metabolism are all considered to be adaptations to its environment. We have time for a third mystery of science. So let's return to space, shall we? Our next one will take us to the planet Venus, which, as you probably know, is at the same time the most similar planet to Earth in terms of size. It is also a rocky planet, but contrary to ours, its surface is a scorching, hellish world. It has a very thick atmosphere that puts enormous pressure on everything. Pressure on the surface is estimated to be more than 90 times higher than on Earth. The main component of this atmosphere is not nitrogen and oxygen like our atmosphere, but carbon dioxide. Between its density and its composition, the atmosphere of Venus creates an enormous greenhouse effect that maintains surface temperatures above 800 degrees Fahrenheit, more than 400 degrees Celsius. That is to say, more than enough to melt metals like lead or zinc. At such temperatures, even with this pressure, there cannot be liquid water, and it is widely admitted that life is impossible at the surface of Venus, at least not the kind of life we are able to conceive. So Venus is a hell, and actually the only concept of human colonization that were imagined since the 20th century are never based on establishing a presence on the surface. Instead, scientists or writers have imagined floating cities that could float on this very thick atmosphere at altitude, where conditions of heat and pressure would be less hostile. But the point is that it probably was not always like this. Scientists believe that there is a fair chance that Venus once had a more temperate climate, and possibly even liquid water, until dramatic changes happened. Why and how? That is our mystery. It is all based on models about planetary formation and extraterrestrial climates, or speculations. But here is a rundown of what Venus's climate could have been like and what could have happened to it. So first, why this assumption that the surface of Venus was once similar to the surface of Earth, or maybe even habitable? Because the planet formed in the first 100 million years of the solar system with similar ingredients to Earth: rocks, metals, especially iron, and a mix of gases. All of this was brought by collisions with asteroids, the absorption of dust, rocks, and gases on their respective orbits over millions of years, and bombardments by asteroids coming from farther away. This is what is believed to have brought to Earth a good share of its water. Another similarity with Earth is the distance to the Sun. Venus is a bit closer, at 72% of the Sun-Earth distance. But like Earth, it falls in what astronomers call the habitable zone around the Sun. This concept of habitable zone is a region around a star that would supposedly be more likely to harbor life because it receives energy from the star, but without being too close to it. And so liquid water could exist at the surface of a rocky planet in the habitable zone, allowing Earth-like kinds of life. Now we have no direct proof that Venus had a mild climate, together with an Earth-like atmosphere that protected its surface without creating too much greenhouse effect or pressure. It sounds possible. By comparison with Earth, similar size, similar formation history, similar materials, but it remains speculative. However, if we accept the hypothesis, especially presence of liquid water, so the existence in the past of oceans on Venus, probably with underwater volcanic activity, providing energy and chemicals, possibly bombardments with asteroids carrying the basic bricks of organic life, not life itself, but complex molecules that can be used by early organisms. This theory of the dispersion of these compounds across space by asteroids or comets is another unproven theory, but it also exists as a possibility. So, for all these reasons, a similar set of conditions on Venus would make the appearance of life on it possible, if not plausible. We know, based on what happened on our planet, that single-cell organisms can remain the only ones and not evolve into bigger, more complex animals or plants for hundreds of millions of years. And that's what it took on Earth for single-celled beings to move past that stage. So even though there could have been life on Venus, it seems that there would still be a high chance that this life would have been rather basic. And there is no proof at all of more complex life, let alone intelligent life. However, if it happened, it was cut short probably 2 or 3 billion years ago. Like Earth, the age of Venus is estimated to be about 4.5 billion years. So the age of possible life on Venus would have lasted a few 100 million years, up to maybe a couple of billion years. But when the climate shifted, it did so dramatically. The leading theory for Venus's transformation is a runaway greenhouse effect, the climate spiraling out of control due to a self-sustained loop of the atmosphere becoming denser and denser and hotter. But what started it? What started this greenhouse effect spiral? The first possibility is the heating of water, a scenario in which Venus would have paid for its closer distance to the Sun than ours, and possibly the presence of more greenhouse gases like carbon dioxide in its atmosphere. In the first 100 million years after its appearance, it is believed that the Sun grew brighter over time, which is a natural evolution for a star of its kind. The increased radiation would have made water evaporate on Venus, possibly to the point of drying oceans. And as water vapor is a potent greenhouse gas that could have ignited the disaster by trapping more heat, accelerating evaporation and rising temperatures always further. Evaporation exists on Earth, obviously, but luckily for us, it doesn't start such a loop because there is enough condensation and low enough temperatures, especially near the poles, to trap water in liquid or solid form. So this cycle of water doesn't stay blocked at the evaporation phase. And this prevents the Earth's atmosphere from becoming always richer in water vapor. There is no feedback happening. If indeed all of Venus's water evaporated, it is well possible that the planet lost it almost entirely, because in the upper layers of the atmosphere, solar radiation can break apart water molecules. Under ultraviolet radiation, water returns to hydrogen and oxygen. Hydrogen and oxygen could then have been carried away by solar wind. This flow of particles and radiation that the sun emits. It is not actual wind like on Earth, of course. Solar wind travels in the void of space, but it is the same concept, with a continuous flow of particles. Here we touch on another major difference between Venus and Earth. Venus lacks a potent magnetic field like Earth. Magnetic field around our planet protects us from solar radiation that gets deviated by this combination of magnetic field and atmosphere that makes life as we know it possible on Earth. So without this protection, Venus could well have lost its water, if it ever had any. We know that today there is barely any water left on Venus. It could obviously not be liquid given the conditions, and the atmosphere only has traces of water. So, if there is water on the planet, it would have to be trapped somewhere under the rocky surface. A consequence of no longer having oceans on a rocky planet is that CO2, carbon dioxide, is going to accumulate in the atmosphere. Why is that? Because volcanic activity releases CO2. On Earth, it gets trapped in oceans, locked in rocks. But if there is no expanse of water and nothing that fixes it under solid form somewhere, CO2 will just accumulate in the atmosphere. And this is what is believed to have happened on Venus following the loss of its oceans. Carbon dioxide would have progressively accumulated in the atmosphere to the point where it now accounts for 96% of it, with a catastrophic impact on the greenhouse effect that would have been greatly intensified. And that mechanism, evaporation, rise in temperature, accelerating evaporation, loss of water escaping the planet, and accumulation of CO2, replacing it in the atmosphere, raising temperatures always higher, accelerating evaporation, and so on, continued until the atmosphere had become so thick and heavy that it no longer allowed any heat to escape. The surface of Venus is kept in darkness because sunlight cannot penetrate its very thick atmosphere and dense cloud layer. But the very limited radiation that passes this barrier, plus the heat from the planet itself, remain completely trapped, explaining the extreme temperatures at more than 800 degrees Fahrenheit. As I mentioned, volcanism with the release of greenhouse gases could have also been an accelerating factor. I mentioned carbon dioxide in particular because it is the main component of the atmosphere. But another potent greenhouse gas present in Venus's atmosphere is sulfur dioxide, and it probably comes from volcanism. Yet another accelerating factor could have been albedo changes. What is it? In astronomy, albedo measures how much light a surface reflects. Albedo is typically expressed with a figure between 0 and 1. At 0, a surface absorbs all light, and so it is perfectly black. A black hole would be an example of that. At 1, it is the opposite. The surface reflects everything, and so it appears perfectly white. Nowadays, Venus has high albedo, 0.75, because it has this reflective layer of clouds in the upper atmosphere. But historically, a low albedo of the planet could have helped its warming. When oceans would have evaporated, the planet would have become darker, with dark lava plains replacing oceans that are more reflective, and the clouds that are typically made of droplets of water would have disappeared because pure water vapor is transparent. So as it warmed up, Venus could have turned darker, another factor contributing to the absorption of solar heat, solar radiation, contributing to the perfect storm that made its climate completely shift. The clouds that give the planet this milky, pale appearance today would have appeared later. They contain, in particular, droplets of sulfuric acid. These clouds reflect 70% of sunlight, and ironically, they cool down the upper atmosphere, but under it, heat is trapped and increases dramatically as one approaches the surface. Probes have explored this atmosphere, of course, but they did not resist long due to the extreme conditions. Now, this scenario of warming snowballing is a possibility, but like I said, it is also very hypothetical. It would be a logical chain of consequences given what we know of Venus's formation, history, and composition. But we have no proof, and there are alternative explanations or scenarios. One is simply that maybe Venus never had the kind of milder climate that Earth enjoys, and we would just be tempted to believe it because it creates a story that speaks to our own condition and our own worries about our planet. It is possible that from the start, Venus never received much water and always had a thick CO2 atmosphere that made it a greenhouse planet since its formation, or slightly later. Or another possible scenario is that rather than a gradual runaway process, there was a sudden catastrophe, a disaster that eliminated the previous atmosphere or compromised the planet. A massive asteroid impact, for example. A worse collision, like the ones that happened apparently at different periods on Earth. Or maybe a volcanic upheaval that would have released suddenly a massive quantity of greenhouse gases are also possibilities that could explain the fate of Venus. We've come to the end of our journey tonight. I hope you enjoyed it, and I invite you to discover and learn more. Now you can let go and sleep. Or if you're not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.